Yesterday we were discussing this function. This graph is the graph of f of x equals x cubed minus 6x squared. And we were asking to identify roughly where this thing was concave up or down. So if you take a look at this nice, neat graph, we're concave down till you get to about 2. And then the curve goes from a sad face curve to a smiley face curve, indicating concave upness. And we were talking about how we can justify that this point where it changes is at 2. And that's where we went to kind of the number line, and we saw that f double prime explains it, that we're concave down from negative infinity to negative 2 and concave up from 2 to infinity. And the reason for this is because concave, if you are concave down, what that means is that the derivative is becoming more negative. So if you think about that, slopes, if they were to begin positive, become less positive and more negative. So you get a sad face curve. If you were talking about, for example, places where the second derivative is positive, that means the first derivative is increasing or getting greater. So if you were negative, what's going to happen is you're going to become more positive, so you get a happy face curve. And so this point at which the action changes from a place where the curve was concave down to a place where the curve is concave up is known as a point of inflection. So what we would say is that 2 comma and the y value would be gotten from plugging in 2 into the original is a point of inflection because f double prime is changing its sign. So we know we're going, in this case, from concave down, concave down to concave up. And so f double prime is changing its sign. So very quickly, I had the class draw a sad face curve and a happy face curve. So like an upside down parabola and a right side up parabola. And then I asked the class to kind of split this up down the middle. We have this part here, the green part, and say we have the black part, and we have the green part here, and say the black part here. And now basically we can identify, if we take a sad face and a happy face curve, split them down the middle, each of these pieces is going to be 2 things, either increasing or decreasing, or concave down and concave up. So increasing means we're going up from left to right. So increasing, concave down, would mean we have to be going up the hill, but we're doing it in a sad-faced way. So increasing concave down would look like this. Decreasing concave down means we're going down the hill and we're doing it in a sad-faced way. So here's my sad-faced decreasing concave down portion. Happy face, concave up. So if we're increasing and concave up, that means we are on the upswing, and we are doing it in a happy way. So here we are. That would be increasing concave up. And then decreasing concave up, we are going down the mountain, but we are doing it as part of a smiley face. This would be a decreasing concave up curve. The reason why we're doing this is now the goal is we're going to do soup to nuts. We're going to graph number 9 in your worksheet. But before we do that, I just want to make sure we understand something. Where is it? In your notes. Just about concavity in general. First, when we want to find out concavity, we need to find f double prime. F prime is going to give us increasing or decreasing behavior. F double prime is about concavity. We set f double prime equal to 0. Okay, and we're going to put those values on the number line. If f double prime is greater than 0, then we know the function's concave up. If it's less than 0, the function is concave down. And then I briefly mentioned this, a point where the concavity changes is called a point of inflection. And for the sign of the second derivative, the sign of the second derivative must change. So the point, whatever the point may be, is a point of inflection because f double prime is changing its sign. So, onward and upward. Soup to nuts. I'm going to graph this function, f of x equals x to the 4th minus 8x squared plus 12, with all the justifications, everything you need to be able to know how to do. First things first, we must get f prime, and we must formulate a number line for it. So f prime of x is 4x to the third minus 16x. And we're going to set this equal to 0. We're going to get our critical values. Usually we also have to watch out for where the derivative is undefined, but there is no fraction here, so we're okay. Factoring out a 4x, we would be left with x squared minus 1. I'm sorry, x squared minus 4. And then we can factor further. And now we will have 3 roots. 1 at x equals 0, 1 at x equals negative 2, and 1 at x equals positive 2. And all of those roots need to go on a number line. So first we're going to draw f prime, f double prime. These roots will go on the f prime number line, negative 2, 0, 2. And I'm going to use the factored form of the derivative. Let me actually. The only problem with this movie is it's going to be a little tight for space. We're going to have our factored form of the derivative is 4x, x minus 2 times x plus 2. And now in order to figure out the signs along the intervals, we need to plug in a value on each piece. So for example, if I plugged in negative 3, 4 times negative 3 is negative. Negative 3 minus 2 is a negative. And negative 3 plus 2 is also a negative. A negative times a negative times a negative will give us a negative along that interval. Now, in my head, I'm going to plug in negative 1. 4 times negative 1 is still negative. Negative 1 minus 2 is still negative. But negative 1 plus 2 is positive. So a negative times a negative times a positive is a positive. So on that interval of numbers, f prime is positive. All right, from 0 to 2, I will plug in 1. 4 times 1 is 4. That is positive. 1 minus 2 is still negative. 1 plus 2 is positive. So we have positive times positive, which is a negative. Last but not least, we will plug in a number to the right of 2, say 3. 4 times 3 is 12. That is positive. 3 minus 2 is positive. 3 plus 2 is positive. Positive times a positive times a positive is a positive. We have now filled in the number line for f prime. We must also now fill in the number line for f double prime. So we will take f double prime. F double prime, I'll just base it off of this f prime, which is 12x squared minus 16. So I will set this equal to 0. Solving this, this one's a little easier to do this way. Move the 16 over. Divide by 12. So x squared is 16 over 12, which reduces to 4/3. Taking the square root, x is plus or minus 2 over root 3. We need to keep something in mind here. 2 over root 3 is smaller than, say, 1, because root 3 is bigger than 2. Actually, I'm sorry, root 3 is smaller than 2. So 2 over root 3, so this is actually a little bigger than 1, but more importantly, less than 2. Okay? So on our number lines, 2 over root 3 needs to go in between 0 and 2, and the negative 2 over root 3 needs to go there. Now again, we're going to plug in numbers, and I would again plug into the factored formula. You can factor out from the derivative. You can factor out a 4 and be left with 3x squared minus 4. A little easier. So our factored form of the derivative is 4 times 3x squared minus 4. What's a little easier this time is to pick numbers. So for example, to the left of negative 2 root 3, we will pick, say, negative 2 works. Negative 2 squared is 4. 4 times 3 is 12 minus 4 is 8. That is positive. Times a positive 4 is positive. Then between negative 2 root 3 and 2 root 3 is 0. So 4 is clearly positive. X squared is 0 squared. That is 0 minus 4 would create a negative. So now on that interval, we are negative. Positive times a negative is a negative. And now we'll plug in a number like 2. 4 is positive. 2 squared is 4 times 3 is 12. 12 minus 4 is 8. That is positive. Positive. Okay. Now, f prime tells us whether the function is increasing or decreasing. F double prime tells us whether the function is concave up or down. So what we're going to do, is we're going to, I want to cover this up, and you can do this with a piece of paper. I'm going to scroll across both number lines and stop when something changes. So right now, we have a negative f prime number line and a positive f double prime number line until we get to negative 2. And that's when things change. So we're going to leave this alone and we're going to just analyze this area. F prime being negative means that f is decreasing. Okay? This means that f is decreasing. And f double prime being positive means that f is concave up. So if you think about what we did before, I gave you guys options. If you split up your smiley, and you split up your sad, decreasing, concave up. So decreasing, we're going to be going down, but concave up, we have to be part of a smiley. Looks like this curve that I'm toggling around. So, I'm going to clone this. Along this interval, that's what the function's doing. It's decreasing, but concave up. So, and at negative 2, it's going to make a change. Okay? And here's the change. Now the f prime number line has become positive. F double prime doesn't change until we get to negative 2 root 3. So now we have another interval. We have an interval where we have a positive f prime and a positive f double prime. So along this interval, f is not decreasing anymore. F is increasing. F is increasing and is still concave up. So increasing concave up is the increasing portion of my smiley face. So it looks like this. So on that interval, we're going to have a curve that looks like that. Now, as we pass negative 2 root 3, we get a sign change, not of f prime, but of f double prime, until we get to 0, where f prime is actually going to change sign. So now, we're on an interval where f prime is positive and f double prime is negative. So now what's happening is the function is still increasing, but the function is concave down. So we're increasing, so we're going up the hill, but we are concave down, so we are a part of a sad face. So this little guy is increasing concave down. So we're going to clone this. That's going to be our next portion of the curve. And what's happening now is we're seeing curve unfold, what kinds of pieces we're going to have. Then at 0, the first derivative changes its sign until we get to, and the only sign change we have after that is going to be on the second derivative curve, the second derivative number line. So now we're dealing with an interval where f prime is negative and f double prime is negative. So now, if f prime is negative, the original function is decreasing. And since f double prime was still negative, we are concave down. So decreasing, concave down, is the going down portion of the sad curve. So we'll clone this, and we'll put it right here. So now our curve is unfolding. If you were to graph this on a graphing calculator, you would see this curve unfold as such. Now we're going to pass the next interval where, let's add a little negative sign here, where now f double prime, whoops, sorry, f double prime, sorry, f prime is still negative. On this interval, if you notice, f double prime is positive. So now we're concave up again, but we're still decreasing. So we're decreasing, still decreasing, but concave up now. Decreasing, concave up. So we're on the going down portion of the smiley face. So we're going to clone this, put it right there, and the curve is unfolding, as you can see. And last but not least, our last sign change overall, we have f prime is positive and f double prime is positive. So since f prime is positive, the original is increasing, and we're concave up. So we are the increasing portion of a smiley face. Clone that, and there we are. So now we can see our curve is unfolding. And at every point where you have some sort of joining happening, we have an important point that we have to address. So in all these stars, we have an important point that we have to address. And I'm just going to write the x values. And I'm going to write a little table. X, Y, what, and Y. At x equals -2, we'll leave the y value blank for a moment. Clearly, you can see at x equals -2, we have a minimum. And we can explain mins and maxes on the f prime number line. At -2, notice the derivative is changing its sign from negative to positive. So f first derivative changes from negative to positive. And we'll pick up the y values, okay, as we go along. At -2 over root 3, we don't have a min or a max. So what we have is a place where the concavity is changing. A smiley face is changing to a sad face. The green smiley part is changing to a black sad face part. This is called a point of inflection. And that can be explained by f double prime changing its sign from positive to negative. So I'm just going to write because f double prime changes its sign. Because for inflection points, it doesn't really matter how the sign is changing. It just matters that the sign is changing. Next important x value is 0. And at 0, we see that we have a max. Because f prime this time, f prime explains mins and maxes, is changing this time from a positive to a negative. Next important point, x value is positive 2 over root 3. And that is not a min or a max, but it's a point of inflection because the red sad face curve meets up with the blue happy face curve. So we have a point of inflection, which I'm just going to abbreviate as POI, because f double prime changes sign. And last but not least, we get to x equals 2. And 2 we can clearly see is a minimum from our little graph. It's minimum because f prime, if we look at our number line, f prime is changing from a negative to a positive. So those are our justifications. We have two things to do. We have to retrieve y values, and we have to graph. So what I'm going to do, actually, is I am going to take this. Maybe I'll pause this for the. All right, so all I did was I just made a new page here. So we get rid of, in class I did this, I did the graph on the board, but obviously we can't record the board. So now we're going to do the full graph. So we need to get y values. The original function is f of x equals x to the fourth minus 8x squared plus 12. So, by the way, if you notice, if you plug in a positive, say you plugged in positive 5, you're going to raise that to the fourth, that's going to give you a positive. And then you're going to raise it to the second, that's going to give you a positive. If you plugged in the negative version of that, negative 5, you're going to get the same answer because raising to fourth and raising to second, you get positive answers no matter what. So I'm just actually going to go ahead and get the values for 0, 2 over root 3, and 2, and then we know we have some symmetry here. So at 0, if we plug in 0 for x, 0 to the fourth minus 8 times 0 squared, or 0 plus 12 is 12. So there's my y value. 2 is easy. 2 to the fourth is 16. 2 squared is 4 times 8 is 32. So now we have 16 minus 32 is negative 16 plus 12 is negative 4. And very quickly, I didn't do this in class, but I will do it here. If we wanted to get the y value at 2 root 3, a little bit of a pain in the neck, but it isn't terrible. It's doable. 2 over root 3 to the fourth would be 2 over root 3 squared times itself. You'll see why I'm doing that in a minute. 2 over root 3 squared is 2 over root 3 times 2 over root 3. Well, 2 times 2 is 4. Root 3 over root 3 is 3. So this is 4 over 3 times 4 over 3, which is better known as 16 over 9. 2 over root 3 squared, we just did, is 4 over 3. So now we get minus 8 times 4 is 32 over 3 plus 12. If I want to make this into one fraction, I would like my denominator to be ninths. So I'll multiply 32 times 3, which is 96 over 9, plus multiplying 12 by 9 is 108 over 9. So now we get 16 minus 96 plus 108. 108 minus 96 is 12. 12 plus 16 is 28. 28 ninths is the y value here. And it's also the y value here due to the symmetry. And the y value here would be negative 4 due to the symmetry. So there are our y values. And in class, I kind of just told the class about the 28 over 9. I'm not that interested that you can do the arithmetic. I'm more interested in the concepts here because there's a lot going on. So I want to erase this. Just talk through it because now we're going to graph this thing. All right. So I'm going to now plot the x and y values of all the important points. Negative 2, negative 4, negative 2 over root 3, comma 28 over 9, which is a little greater than 3, 0, 12, positive 2 over root 3, comma 28 over 9, and then positive 2, comma negative 4. Those are our important points. And if you notice, we're going to connect them just as we have up here. We're going to connect them just like this. Okay? That's how we're going to connect those points to get a nice accurate graph here. We're going to connect them just like that. So from negative infinity to negative 2, we have this decreasing concave up curve. From negative 2 to negative 2 over root 3, we have the increasing concave up curve. Then we have the increasing concave down curve. Then we have the decreasing concave down curve. Then we have the decreasing concave up curve. And then we have the increasing concave up curve. So our final graph looks something like that. And you can see at this point is the change. This is an inflection point. It's the change in concavity. Here we have the change in concavity. And there, if you were to produce that on a graphing calculator, our graph would look very, very similar. So this is what we did in class today, plus I gave the group a problem to do to count as a quiz grade. You guys will have to make that up if you were absent, but this is what we did in class today. So you are effectively caught up. If you have questions, please come and see me. We're not spending time on this tomorrow in class.